This video is going to be an introduction to the topic of chemical kinetics, and we'll look at how rates of reaction can be measured experimentally and determined using graphs. So a quick summary of the topic is that chemical kinetics looks at the speed at which chemical reactions take place and how different factors affect that speed. The main things we're going to look at are things like surface area, concentration, temperature, and the presence of catalysts. The theory that we'll use to explain why these changes affect reaction rate is called collision theory. And other components of this topic look at how we measure reaction rate experimentally and what the graphs look like that we create with those methods. So to start off, the rate of a chemical reaction is defined as the change in concentration per change in unit time. So the technical unit of reaction rate ends up being moles per dm cubed, which is the unit of concentration. And then usually it ends up being per second with the reactions that we look at, although technically this could be any unit of time, like per minute. So we can also look at it a bit more specifically. We can look at the decrease in reactant concentration per time, or we could look at the increase in a particular product concentration per time. And in those cases, we'd get negative rates of reaction and positive rates of reaction, respectively. The following is an example graph. If we started off with all reactant A converting into product B, over time, we would expect the amount of reactant A to decrease and eventually go to zero if this reaction goes to completion. And we would start off with zero product, and the product would be formed as quickly as the reactant is used up, and eventually the amount of product would stay constant, and that would be the completion of the reaction. So these two curves are the most common shapes that you're going to see on graphs in this topic, where you have the rate, either something increasing over time, concentration increasing over time and eventually leveling off, or a concentration or an amount going down over time and eventually leveling off. Now, the exact reason for that shape we'll get into later when we talk about collision theory, but for now, just become familiar with these two shapes and be comfortable drawing them. Now, experimentally determining reaction rate is where we're going to start, because this is how we can actually do this in the lab. So the key with any reaction is finding something that's measurable that will change over time. The best methods involve monitoring a reaction continuously. So picking out some sort of variable that you can measure at a given time interval, like every second or every 5 seconds, that allows you to monitor the progress of the reaction in real time. So the most common examples would be like measuring the volume of gas that gets produced by a reaction. You could do this with a gas syringe, hook your reaction, seal your reaction off, connect a tube to a syringe, and as the gas gets produced, the syringe will push out the plunger and you can actually record the volume of gas over time. You can also collect gas in an upside down graduated cylinder that's been filled with water, and you can measure how much gas has been made at regular intervals. You can use a pressure probe to measure the amount of gas produced. More gas will mean more pressure. You can look at the mass of the reaction container over time. If you're producing a gas, then the mass of the container will decrease over time. For reactions that involve color changes, you can measure the absorption of particular wavelengths of light, and that should change according to how dark or how light the solution is. You can look for certain reactions at how conductive the solution is based on if the number of ions in the solution is changing. And if the amount of H plus ions is changing, then you should be able to use a pH meter to detect how quickly the reaction is progressing. There are also going to be non-continuous methods that we can use. We especially use this with color changes, certain color changes, where we measure the total time that it takes for a particular change to happen. So a famous example is like the iodine clock, where after about 10 seconds, the whole solution just turns to a dark black color all at once. There's no way to monitor that color change continuously because it happens in an instant. So we can just measure the total time that it takes, and then that can be used to get a sense of the average rate of reaction. We could also look at how long does it take for a particular solid to completely react, to go from being a solid to being totally dissolved and reacted away, instead of monitoring something continuously over time. So mostly what we're going to look at are reactions that produce gas. They're probably the easiest to monitor. We'll look at reactions that involve color change. So it's helpful to be familiar with certain species that have color, like copper 2+, which we know is blue, iodine, which is sort of reddish, bromine is sort of reddish. Most transition metals have some sort of color, or the iodine starch complex which it has a very dark blue color. So those often get used as examples on the IB exam because they allow you to mention a colorimeter as a method of measuring the reaction rate. And then reactions that involve changing in the moles of ions from the reactant side to the product side are ones where you could use a conductivity meter to measure the rate of that reaction. So if you monitor something in a continuous way, and in this example, we're measuring the volume of gas collected over time, this is an example of the type of graph that you might get. Now, why that's helpful is that if we're looking at the volume being produced over time, then the rate of change of that graph is going to represent the rate of the reaction. So to get the rate of change of a graph, you want to get the slope. So if I want to know the rate of reaction at any one given point on this graph, then I need to draw the tangent line to this graph at a particular point. So at the time in question, so let's say it's at time 10 seconds, we want to know the rate of reaction. We draw a tangent line to the curve at that exact point, and then we would have to figure out the slope of that line, which you've probably done at some point in your math career, which would be you pick 2 points that you can readily identify. It could include the actual point itself. So at 10 seconds, we're at about 35 mLs collected, and then we could go all the way out to, at 20 seconds, we're about 65 collected. So we could see that over those 10 seconds, we changed from 35 to 65, which is a change of 30 mLs. So 30 mLs per 10 seconds, that's going to be 3 mLs per second. So 3 milliliters of gas are being produced every second. And that's the rate of reaction at this time at 10 seconds. So to know the rate of reaction at any instant, we get the slope of the tangent line at that given point. We can also use these continuous curves to find out the average rate of reaction for the whole reaction. So this is when the reaction starts, and when the thing plateaus and we get a slope of 0, that's when the reaction is over. So this is like the end way out here. And so if I wanted to know the average rate of reaction, then I would want to try to draw a line from the very beginning to the very end, and I would get the slope of that line. And so the slope of the line from the very beginning to the very end would represent the average rate of reaction. So the slope of the tangent line at a given point over here, that's the instantaneous rate, and then this is the average rate. Right? Now, the key takeaway there is that slope on a graph is going to represent rate of change, and in these types of graphs, it's going to represent rate of reaction. The non-continuous methods we talked about, like measuring total time for something to happen, it's a little more limited. All we're really going to be able to get from that is a sense of the average rate of reaction and how it compares under different conditions. So what you would do there is you would take that total time, which is reaction time, and in order to make it a rate, you would actually invert it. So you would do 1 divided by the reaction time, and that would give you a unit of per time, usually per seconds. And so it would tell you, how much of it is happening per second. So you'd be turning it into a per second, which is a way to describe rate. Any rate will always be per a unit of time. So with the non-continuous method, you're talking about taking the time and getting the inverse of that time value. So longer times will end up having smaller rate values because they're happening more slowly. So that's an introduction to rate of reaction and how we can measure it experimentally, and then how we can take that experimental data, we can plot it and make a graph out of it, and we can get different values like the instantaneous rate or the average rate of reaction.